Mr. Professor Charles Elachi.
For thousands of years, our ancestors, your ancestors, my ancestors, looked at the sky and wondered, what are the stars made of? What are the planets made of? Is there life somewhere else? Is there another O2 in the sky, on another planet? And basically, if you look at the picture that is in front of you, this is what the sky looks like in a large telescope, about an area about the size of a euro at the end of your hand, that little teeny part of the sky. That's what it would look like. It has basically thousands of galaxies, and each galaxy is made of billions and billions of stars. So it's amazing, the universe around us. What is it made of? And the question is, how did it come about? How did it get created after the Big Bang? What is it made of? So what we are trying to do in our exploration is to write what we call the book about how did that happen. And what's amazing is around one of those stars, a star called the Sun, actually planets formed. And on one of those planets, it had the right ingredient, the right chemistry, the right temperature, that it led to life and to people like you and I are sitting down today having this discussion. So the question is, how did that happen? And what I'm going to tell you today is about one chapter, just one small piece, of what we have discovered, what we are planning to do, and particularly important to the audience here, the kind of people behind. How do they actually achieve what seemed to be impossible? So I'm going to be focusing on the planet Mars. And the reason we focus on Mars is, number one, it's one of the closest planets to us, so we can travel there. It still will take us 9 months to get to Mars and 9 months, to come back. It's a planet which is very similar to our own planet with differences. As you look at the picture here, Mars is about 1/4 the size of the Earth. So if you take the oceans away, the land mass on Earth and the land mass on Mars is about the same. Mars has an atmosphere, much less than our atmosphere, but it has an atmosphere. It has polar caps. You look at the bottom of the picture to the right, that's a polar cap, which is made of H2O. So not O2, but H2O, but at least you are part of it. And it has nitrogen on it, and it expands and shrinks depending on the season, on Mars. If you look more in detail, the picture to the right is a Grand Canyon on Mars. The picture to the left is the Grand Canyon on Earth. You cannot tell the difference. I could have told you Mars is on the right and Earth on the left, or Mars is on the left and Earth, and you would have believed me. Earth, we have volcanoes on Earth. There are volcanoes on Mars also. The one on the left is a volcano in California. The one on the right is Mount Olympus, which is a volcano on Mars, which is twice the height of the Himalayas, of Mount Everest. So clearly it indicates that sometime in the past, there was a lot of geologic activity which created, that mountain. These two pictures, I give that as a test to my students at Caltech. I tell them, guess which one is Mars and which one is the desert in California. So let me do a test. How many of you think the picture to the left is Mars? I see a bunch of hands. How many of you think the picture to the right is Mars? I see a bunch of hands. To be honest with you, I forgot which one is which one. But if you were careful attention, if you look to the right, you see a little snake. So that's how I can tell that this is Earth. And the reason I show this picture, the message I want to tell you is Mars is very similar. The geology on Mars is very similar. The material on Mars is very similar. So when we actually send astronauts to Mars and they land on it, they think they landed in California, on the desert in California. So there is a lot of similarity. So the key question we're trying to do with our mission is to see, okay, if Mars was very similar, we actually did find that it had water on it, which is frozen below the surface. Could life have evolved? So these are the kind of missions that we're conducting. So as we speak today, we have 2 rovers which are roving on Mars. They are the size of about your car, And one of them has been roving for about 12 years, and the other one has been roving for about 4 years. And basically, they are driving around, and like a geologist who goes and does an exploration, they are looking at what Mars is made of, what the material composition is made of, and I'll be telling you a little bit about some of the results that we have gotten. This is an actual picture of Curiosity. That's a rover we landed 3 years ago. Now you say, how it was taken? Well, it's the same when you buy an iPhone. The first thing you do, you take a selfie and you send it to your mom on O2 network. And you say, look, Mom, how good I look. So that's exactly what happened. After we landed on Mars, the first thing we did, the rover had an arm. It stuck the arm out. It had a camera on it. It took a picture of itself, and it sent us a picture. So we can say, hey, I landed safely, on the planet Mars. So it acts like a human. And what you see as a background is the Mars actual picture, nothing fake. These are actual color, actual pictures. And this, for a geologist, this picture means a lot, because what it tells us, it looks for me like a dry lake. That means there was a lake which deposited layer of sediment, and then as the water evaporated, you see these layers that you see in there. So that's an indication to us that actually water existed a few billion years ago on Mars, and then the water either evaporated or condensed below the surface and froze because the temperature on Mars changed. So again, the question is if there was water on Mars, and as I will tell you in a minute, Mars has the same materials that are in your body, could have life evolved? And if it evolved, how far did it evolve? And if it did not, why not? Why did on Earth life evolve, and here you are sitting in this room, and on Mars it didn't evolve? So that's the key question we're trying to answer. This is another example. This was taken just a couple of weeks ago, so I pulled it out from our file. So it looks like any desert, in Northern Africa or Saudi Arabia. So you have the same kind of phenomena, and you see to the right corner, that's one of the wheels, of the rover. And basically what we do every day, the rover drives around, looks at rocks, examine them like a geologist does when the geologist looks at rock. It has a magnifying glass, so it put it on the rock so we can see more in detail. And it has a drill, so we actually drill in the rocks, take some of the material, put them in an oven inside, the rover. We heat the material and see what gases are emitted. We have an X-ray machine similar to what's at your dentist when they take X-ray of your teeth, except much more expensive than what your dentist have. So it has all the chemical analysis equipment that you would find at the university in here, all condensed into a rover, which is the size of a car, and then the data is transmitted, back to Earth. So to make a long story short, we found out that every material which is in your body actually exists on Mars. The carbon, the hydrogen, the phosphorus, the nitrogen, everything which is on Earth which led to life exists on Mars. We did find some organic molecules, short molecule, but we still have not detected life. So I don't want to see the headline tomorrow saying life was discovered on Mars. We still haven't gotten to that stage. So that's what we are actually searching for. And the next major step we're going to do, we're going to go and climb along these mountains. These are mountains which are about 3,000 meters. So we're going to climb up the mountain. And what is interesting, you see all these layers, that you see in the picture. That basically, for a geologist, that says that the layer at the bottom is older than the next layer, which is older than the next layer. So as we're driving up the mountain and sampling all these layers, it can tell us what happens through the history on Mars. What happened 4 billion years ago, 3 billion years ago, 100 million years ago, 10 million years ago, as we walk up and basically look at the history of what happened in Mars. And who knows, we might find fossils at a certain time, or we might not find them. So that's what exploration is about, is learning about how another planet evolved at the same time as our planet. Now, let me tell you about the technical challenge, that you need to do to be able to get to Mars. When we sent Curiosity to Mars, after traveling 225 million kilometers, we had to land in a circle which is about 2 kilometers wide. Because if we come too shallow, we bounce. If we come too steep, we burn. So we have to come within that 2 kilometers. Now you say, okay, what does that mean? So I try to do an illustration. It's the same if I go outside of my office in California and hit a golf ball toward Bratislava. The golf ball has to go straight in the cup. That's how accurate we have to navigate our spacecraft. Now, to make it a little bit more challenging for the good golfers, the cup is moving because Mars is moving. And we still have to land inside that cup. So people first said, well, that's impossible. How can you do that? Well, people with innovation and imagination developed technique to actually navigate the spacecraft and make it so accurate that it can land straight on the dime, in that location. Let me give you another challenge. When we are traveling to Mars, we are going at extremely high speed. And at that speed, some of you are engineers here, if you look at the energy, 1/2 mass multiplied by velocity square, that's the equivalent of 18,000 race cars going at full speed. That's how much energy we're coming in. And we have only 7 minutes to slow down and land softly on the surface. Otherwise, you crash in doing that. So we had to come up with all kinds of techniques. We have to use first, and I will be showing you in a video, we had to use a heat shield first to slow us down, like when you are in a car and you put your hand outside the window, the wind kind of blows you back. And that heat shield, at peak deceleration, the surface gets hotter than the surface of the sun, and it still has to survive. Then after we slow down a little bit, then we open a parachute at supersonic speed, the largest parachute which ever was open. That will slow us down a little bit more. Then we have to use a retro rocket to slow us down even more, and then we hover and sky crane down the rover to the surface. And that's what you are going to see in the video. So I'm going to take you now and transpose you as if you are sitting in the mission operation room at JPL at the time when we were landing that rover. And the reason I wanted to show you that, just notice the age of the people. They are kind of like you. They are your age. They are a bunch of engineers who were very dedicated, worked for 8 years very hard to do something which seemed impossible. Matter of fact, when we first went to NASA headquarters and explained to them how we're going to land, they said, you guys are crazy. You must be smoking something in California, which is illegal in the rest of the United States. Go back. But, we sat down and worked and convinced them that what we are doing is not as crazy as it seems, and we did all the modeling and calculation and so on. And to add to the pressure, as you will see, the nervousness of the people, we knew there were 50 million Americans on our website watching at the same time with us to see what the event is happening. So let me run the video, and then I'll tell you more about it at the end.
Coming up on entry. Vehicle reports entry interface. At this time, it will begin pressurizing the propulsion system to increase the thrust of the system. We'll use that for all the maneuvering in the atmosphere we're about to do. The vehicle has just reported via tones that it has started guided entry. We have seen peak deceleration. We should have parachute deploy around Mach 1.7. Parachute is deployed. We are decelerating. Heat shield has separated where we found the ground. We're down to 90 meters per second at an altitude of 6.5 kilometers ascending. Standing by for batch separation. We are in powered flight. We're at altitude of 1 kilometer ascending. Standing by for sky crane. Sky crane is started.
Single dive, you remain strong.
Touchdown confirmed. We're safe on Mars.
Needless to say, thank you. Needless to say, it was a very tense evening, and I don't tell that to too many people. Actually, I had two speeches in my pocket, one if we are successful and one if we fail, on it, because there was a possibility of failure. I mean, everything has to go right. And we could not joystick the lander because it takes 7 to 12 minutes for the signal to come from Mars to Earth. So when we actually said we reached the top of the atmosphere, the rover had landed. We didn't know if it crashed or if it's successful. So, and there were almost hundreds of events, actuators, parachute have to open, everything has to happen right and in sequence. And you could imagine after 8 years of work, if one thing goes wrong, it's like everything is gone. But it was worth it. That allowed us to push the limit and really be able to do something better in exploration. And we felt that that was worth it, even with that risk. Now, let me tell you what's the next major step we're going to do, which is even more challenging. As we speak, we're building another rover, similar to the one you saw, except what this one will do, will drive around and look at rocks which are interesting, drill in them, collect samples, put them in a container, put them in one location. So later we can send another lander with a rocket on it, grab the sample, put it in the nose of the rocket, launch the rocket in orbit, and then send another spacecraft to rendezvous with it and bring the sample back. Piece of cake. Not a problem to do that. But again, these are the challenges. I mean, it's similar to the other people that you heard earlier. I mean, they took a very tough challenge. They didn't know they can achieve it at the beginning, but they worked hard to it. They were imaginative. They came with new ideas, and they got support, of their colleagues, and they were able to achieve that. Now, we are going to add an additional twist to this one. We are going to add a little helicopter, to it, because it makes it much easier for us to operate the rover if we can fly in front of it and survey the area to find which area is particularly interesting, so we can send the rover in that direction. Because it's hard to see it from the rover itself, because the rover is about my height, and we can see maybe about 100 meters. But with a helicopter, we can actually see many hundreds of meters. Now, you say, what's the big deal? My kid built helicopter here. The challenge here is that on Mars, the atmosphere is 1% of the pressure on Earth. So it's like building a helicopter flying at 30,000 meters, higher than airplane actually fly. And that actually had to be completely autonomous. So all the electronics, everything, the cameras, the autonomous landing, all has to be done in 1 kilogram. So that turned out to be a very big challenge of developing the electronics and all the things which enable us to do that. So that's the next thing we're going to be doing in 2020. So if you invite me in 4 years from now, I can tell you how this one actually went. And the other thing we're going to do is to capitalize on the advances in virtual reality. Today, the way we operate our rover, we have scientists around the world, and basically every day they get on their computer and they get on the phone, maybe they use O2 here in Slovakia, and they actually sit down and debate on the phone of the images. They have the image in front of them, and they decide what to do next. With the next mission, we will be able to have Google glasses, or kind of glasses, which they put on, and anywhere around the world that you can walk around and you'll be transposed as if you are walking next to the rover on Mars. So you actually will be seeing the images in front of you, and you are walking and you turn around and you can see the scene around you, and you can discuss that with your colleagues anywhere around the world. And in that way, then you can decide, well, we want to drill in that rock. Command goes up straight to the spacecraft, and the spacecraft decide to do that. And then also the public can participate. You can get those same thing. I mean, you need to do certain communication protocol and network, and you can be sitting here and walking with the rover as the rover is driving on Mars. So that's kind of the next way of how we do, or we're planning to do exploration. So now let me end with 3 charts, because people always ask me, what kind of people work at JPL? What kind of people you look for that can do these things? Well, these are people like you. And we look at 3 characteristics. You look at that picture, guess which one is a JPL employee? Is the one who's looking completely differently than all the other people are looking. And basically, the point here is the message is the same thing as you heard your CEO, here earlier. O2, when it came to Slovakia, you didn't do the same thing that the other company did. You came with something different, to do that, which, made it more attractive. So the same thing here. My message to you and to the employees we do, don't look like everybody is looking. Don't try to do the same thing that everybody is doing. Try to look differently and look at something different and explore a new way of doing things. Now, I'm not advocating that they come to work tomorrow without a shirt on it. All what I'm advocating is think differently than the normal people, because that's how you open a new frontier. Because if you think like everybody else, you're not doing anything new, you're not opening any new frontier. You have to look differently on that, even if things might not work the first time. The second point I make, we celebrate. When we have successes, we celebrate, and even when we have failure, and we had few failures, we also get together and have a party to thank the people which have worked on it, because people are trying to push the limit, and when you explore, every explorer had failures in their career. There is no way you can do exploration and every time you are successful. That means you are not exploring, you are not trying hard enough. So failures actually do happen, and you have to celebrate them. And it's everybody which celebrates. You see me at the back with all the senior people, at GPL. We're celebrating with the employees. In this case, it was a good success, so it was a great celebration. But we also sit down and celebrate about when things don't work. And the last message I want to leave with you is my favorite quote. And I'm going to leave it for a minute and actually read it for you and then describe it. It's from Teddy Roosevelt, who was a president in the United States about 100 years ago. And it says, it's far better is to dare mighty things, to win glorious triumph, even though checkered by failure, than to rank with those spirit who neither enjoy much nor suffer much, because they live in the great twilight that knows not of victory nor defeat. So if you sit down and you stay in the twilight and you are afraid of failing, you'll never progress. And if you don't try new things, you'll never advance. So it's far better to try mighty things, even if you might fail, because then when you succeed, you will see how the great pleasure, I'm looking at some of the people who have achieved. When you succeed, it's amazing what you feel. And even when you fail, you say, okay, next time I'm going to try harder. So my final message to you, make sure you dare mighty things. Thank you very much.